Welcome you all to this course. Today's class I am going to discuss about the electromagnetic lens system. So we all know that lens systems are very important for focusing the electron beam. Previously we discussed about this lens system and how image formation is happening using a glass lens, but for electron microscope mostly we have to use the electromagnetic lens system, otherwise we cannot converge the electron beam because glass lens is not capable to converge or diverge the electron beam. So, if we want to converge or diverge the electron beam, definitely we need a electromagnetic lens, and that electromagnetic lens it will help us. So, today's class it will be mostly focusing on the electromagnetic lens. So far we know that glass lens, gun lenses from electron microscope that we already discussed. Now let us talk about rest of the lens system. What kind of lens do we have? If we just consider here, so electromagnetic lens. So if we just remember, I started with a filament, that is my filament. So I'll just change the color here, and first this time I'll draw the optical axis first, then I'll not do the mistake because previously it was not very straight line. So this is my optical axis, and the optical axis will be very straight. Now if I just consider first, it will be first anode, and then there will be a accelerating stack. We already discussed about the accelerating stack, which is helping us to accelerate the electron. Then it is coming to the first lens system. If we have the first lens, it is called the condenser lens 1, right? Then it is coming to the next lens system, that is condenser lens 2. In 200 kilovolt microscope or 120 kV microscope, most of the cases we have only condenser lens 1 and condenser lens 2. For 300 kV microscope we have condenser lens 1, condenser lens 2 and condenser lens 3. So at this moment we are considering this is a system of 200 kV or 120 kV. So mostly you can see condenser lens 1 and condenser lens 2. Then you will get a objective lens which is connected with each other. So objective lens, so one objective lens, if you just consider this objective lens, it is called the upper, this is upper objective lens, and this is the lower objective lens. So this is upper objective lens and this is the lower objective lens, and this objective lens is the most important lens system because here our sample will stay somewhere here. So that is the first part where electron beam is going to interact with our sample. So far gun lens, if we just consider this is our gun lens, this is our gun lens, then our condenser lens system, then it is interacting with our sample. So most of the time when there is a light source is there for light microscope, it will directly first interact with the sample and then objective lens and our eyepiece and other thing. Here first electron beam is coming out from the gun lens, then it is going through the accelerating stack, increasing the speed, then it is going through condenser lens 1, condenser lens 2, and then it is going through the sample. When it is going through the sample, after that when electron beam it will come, it will go through multiple other lens system and it will give us an image at the image plane. So if you just consider, there are total 6 lens system we are using, 6 lenses system we are using to get an image. It is not like that for light microscope. Whenever we are required, we are changing the lens completely. Here lenses are fixed, we cannot change the lens whenever we want. What we can change? We can change the magnetic field of that lens or electric field of that lens. Those lenses are called electromagnetic lenses. So if we change the magnetic field, we can change the crossover point of that sample. So that focus point or whatever we are discussing, that we can change it. So let's take a look how it can form a simple image. So if you remember the first class what I was talking for the normal light microscope, how it is forming an image. If this is a optical axis, if we have image here, if we have a glass lens here, rays will go like that. This is the center point. One ray it will come, one ray it will go through the focal point and it will merge somewhere and it will give us an image. So electron microscope also is going to work in a same way, and that is the reason initially we discuss about this optical lens system or glass lens system, how it is working. So if this is my object, this is my image. So you can see that image is basically inverted here. Image is basically inverted in this particular direction. So the rays will come and merge here and it will give us an image. So always inverted image and it will be a bigger size. Now for the electron beam, what kind of images do we get? Let us see. So if we just consider there is a source, point source, it will come like that. We have a lens system like that. When the electron rays are coming, it will converge in one particular point. So if we just consider there is no object here. So in this particular case there is no sample, no. So I remove that one. So electron beams are coming and converging in one particular point and it is D0. And then electron beams are changing their path length. They are converging, diverging and going like different path. Finally they are converged in one particular point. So you can see if we don't have any sample, if it will constantly converge and diverge, and it is merging in one particular plane here, we'll get a dot again. So if we are starting from a point source and we can image a point source at this particular point, or what we can get it if we are using a stronger magnetic field, that so this is my magnetic field. So magnetic field is working like that, it is pushing that rays. So if we have a stronger magnetic field, what will happen? Beam may converge somewhere here and it will go all the way and give a diameter of that beam. So it may be possible that it is merging in one particular point and giving the same point source, or if we are using a different kind of magnetic field, if crossover point will go up and then you can get a spreaded beam. So you can measure the beam diameter from here. So in this particular case you can see these magnetic lenses, these electromagnetic lenses are fixed. It is not like a glass lens like optical microscope. Whenever I want, I can change the position of that glass lens and get a magnified image. But in this particular case, those electromagnetic lenses are fixed, what we can change? We can change the magnetic field only, electromagnetic field only, which is change the crossover point. This crossover point it will change. So this crossover point can go up and can go down, and it will change the size of the beam. It will be sometime at point source, sometime it will be spreaded beam. Okay. So this is the very basic part of that electromagnetic lens. Let's take a look, go a little bit deeper about that electromagnetic lens system, how it is working. So in electromagnetic lenses, first let's discuss about how this thing is working. So if we just consider that, okay, we have a magnet, it has a north pole, it has a south pole, and there is a magnetic field. Sorry, I draw it in a wrong position, I will just redraw. So here you have a magnet, you have a north pole and you have a south pole, and there will be a magnetic field, right, as a magnetic field. So now if we just consider that you have a electron, and this electron is trying to enter this magnetic field. It can enter in this direction, it can enter in this direction, or it can enter this direction. Now when an electron is trying to enter in a electric field or magnetic field, it will face some kind of forces, right, and that forces, if we just tell that, okay, so at beginning, so if we just consider that this is the force it can face at there is no speed of the electron. At beginning it will face a force that is called charge into its electrical field, so it will be negatively charged. So based on that electric field, it can face this kind of force. Now as I mentioned that if that electron has some velocity and it is trying to enter in this magnetic field, and due to its velocity and motion, it will face another force, and that we can tell that is we can mention that it is a magnetic field. It can field E, it has a velocity and then magnetic field, because this magnetic field we can mention it as a B. So here you can see that there is a force, it is coming from the magnetic field and the velocity, and both has a particular direction. The magnetic field has a direction and velocity also has a direction. So if we just consider the total force what an electron can experience when it is entering in a magnetic field, and it has some motion, it has some velocity, so it can feel the total force, it will be Fe plus Fm. Now I can tell E plus E, V and B. Now if we just take this one, we can get it, and within parenthesis you can see this is a cross product of two component, where what is the velocity and the magnetic field. So it is very simple that, okay, so if the magnetic field it is going in this direction, and if one electron is trying to enter, and if it will enter and if there is no velocity, it is not going to change the magnetic field or electric field in the surroundings area, and it has no effect. But if has a velocity, then it will face some kind of forces, and that we can calculate from this one, that this is called the Lorentz force. or Lorentz theory, that is telling us that if the electron is entering in a magnetic field, how it will, what kind of force it will feel. So, in the electromagnetic lenses, we are not applying any external electric field. So, we can just ignore this particular term, and here when an electron is entering in this magnetic field, it has a certain angle. So, if something is parallel or perpendicular, or if has certain angle, the movement of the electron, it will be different. Okay. So, in this particular case, if we just consider that, okay, if we can ignore this one and the sign symbol, if we just ignore, we can tell that, so this will be the force that E V B into sine theta. So, now when an electron is entering in this, if sin theta equals to 1, also that electron, it will feel another force, that is called the centrifugal force. So, centrifugal force, we can tell that mv square by r is the centrifugal force of electron when it is a spiral motion. And if the angle when it is entering in the magnetic field, if it is in a certain angle where the sin theta it will be 1, then what will get it? So, these two force, when it will entering in the magnetic field and the centrifugal force, it will be same. So, it will be mv square by r. From this one, we can calculate the distance of this incoming electron, what spiral motion or what will be the radius of this radius of the electron when it will follow a certain trajectory and when it will go through this magnetic field. So, in this particular case, you can see, so EB equals to mv by r. So, from this one we can tell r equals to mv by EB, which is depending on the mass of the electron, velocity of the electron, and the charge of the electron and the magnetic field. Okay. So, let us take a look first how the electromagnetic lens look like. So, here I am showing you a diagram about the electromagnetic lens. This electromagnetic lens okay. So, this is a basic diagram of electromagnetic lens where you can see that there is a two rectangular shape architecture is there. So, basically electromagnetic lens, how we are making it, there is a copper wire and there is a width of the copper wire and bunch of copper wire are winding very tightly to a soft iron, which is when the electric current will flow through that copper wire, it is generating a magnetic field and we are measuring that magnetic field here. So, in this particular case, if you look at, there is a casing, this casing is made by iron and that is a soft iron pole piece. This is called the pole piece, this rectangular shape. And now, as I mentioned that there is a copper wires are winding very tightly to the soft iron. So, those are the copper coils and this is the cross section of that, where you can see multiple copper coils are located in this soft iron pole pieces and that will be uniformly distributed for both the part. Now, there will be a water supply, that water supply it will be outside of this soft iron pole pieces. The soft iron pole pieces, when there is this many copper wires are there and we are applying a electric current, it is generating a huge amount of heat energy because of the resistance, and whenever there is a heat energy is changing the diameter of the wire, which is going to change the electric flow of this wire, and that is going to affect our lens power. So what we are telling that in this particular case we are just changing the magnetic field to converge and diverge the electron beam, and if there is a flow of more electric current which is changing the magnetic field of this lens system, which is going to change the power of that magnetic lens, and simultaneously it is going to change the converging and diverging property of that lens. So that is the reason we need a flow of water outside the lens system, so it can maintain the temperature of this soft iron pole pieces. It should not increase the temperature. Here you can see this is the pole piece gap, and this is the bore between these two soft iron pole pieces, and the magnetic field is coming from this region, which is helping us to converge or diverge the electron beam. So this is the overall architecture of a electromagnetic lens. Now electromagnetic lens, this is a very simple diagram, and there is a many different varieties of electromagnetic lenses are there. If you remember first when I was showing the entire column of the electron microscope, there I discuss about couple of points that okay, we have a condenser lens system, we have an objective lens system, then we have projector lens, intermediate lens. Simultaneously I discuss about there are couple of other things are also there. There are any lens is a combination of a electromagnetic lens, then there will be a stigmator, there will be a deflector, and then there will be a aperture. So any lens, these four component, this electromagnetic lens, these four components are very important. So electromagnetic lens, deflector, stigmator and the aperture. Now what is that deflector and stigmator? Deflector and stigmator basically trying to maintain the electron beam through the optical axis. If we just consider this is the diverging electron beam which is converged in one particular point, here near the gap region the magnetic field is helping to converge this electron beam in this particular point. But if there is any deflection of this electron beam, if it is not coming through the optical axis, who is going to regulate that one? So basically deflector is going to regulate that electron beam and it is bring back through the optical axis, as well as the stigmator. If there is any artifacts or any aberration is there in that in the magnetic field, the stigmator will help us to correct that aberration. So here you can see the stigmator as well as your deflector, it is deflecting the electron beam, it is changing the aberration of that electron beam. So definitely those are also having some kind of magnetic field or electromagnetic field which is helping to change the beam. So that is the reason I told this is one of the simplest lens. So there will be a lot of complicated lens will be there. So there will be a quadrupole lens system, hexapole lens system, octapole lens system. For different purposes we can use different kind of lens system. So here this is one of the image of that electromagnetic lens, where this is the outer surface of that lens. If you go inside you can see there will be a copper wire winding tightly. So this is a real lens, the cylindrical shape, the copper wire coils, the two conical pole pieces beside the lens sit inside the central hole of the lens system. So now here you can see these are basically packed here in this particular region. Now let's take a look the actual diagram of different types of lens system. Here I am showing you a objective lens. If you just go through this one, you can see this is the objective lens system. When I was drawing the objective lens, if you remember, I was always talking about upper objective lens and lower objective lens. So objective lens I am splitting into two half. So if you just consider, most of the time I did it like that. So this one is a C1, then this one is a C2 lens system. Then when I came to objective lens, I connected them like that. So I am making some kind of connection of the objective lens, and I told that okay, this is a very important lens because sample will stay in between these two lens. So if you just consider, this is our upper objective lens and this is our lower objective lens, and electron beam first time fall on this sample from the condenser lens 2. So this is going to regulate the electron beam, how much electron beam is going to fall on your sample. Is it going to spread it all over like that, or you are trying to make a sample and focus in one particular point, not it is exposed the entire beam. So there is a two possibility. Electron beam can follow this crossover point and illuminate the entire sample, or we are using a crossover point in such a way it will just focus on the sample. So here, based on these two lens system, we can regulate this electron beam. So what I was drawing here, this is the objective lens. This objective lens, if you look at here, this is our objective lens, where you can see this is the upper objective lens and this is the lower objective lens. These two objective lens are connected like this one. So here you can see this is the opening area where the electron beam will pass and which will regulate that electron beam. Now as I mentioned, this is another type of lens system. It is not very frequently used nowadays. So there is a two different type of microscope is available. One is top loader microscope, means you are loading your sample from top of the microscope. And most of the recent microscope, what we are using a side entry holder. So means if you remember in the microscope column, starting from the gun, then condenser 1, condenser 2, and then there is a goniometer or stage, where I told that if this is the goniometer, here is the goniometer, you are using your holder and inserting the holder here. So this is the side entry holder. There are some microscope where there is a top top entry. So this is one of the lens where we are using the top entry sample loader, where you will drop the sample somewhere here. This is a one kind of special lens for the top loader sample holder. Now there is another very important lens system is there, that is called the quadruple lens. That is, I was talking about the quadruple lens, basically helping us to correct any kind of aberration, that is stigmator. We are using the quadruple lens where there is a south north, north south is connected like this orientation. So there is not like that, okay, only one side is north and another side is south. It is a connected with south and north simultaneously. So this kind of lens we are using for quadruple lens system. So in this particular lens, as I mentioned, specifically we are using to correct the astigmatism. Also there are some lens systems are there, that hexapole lens system, that is 6 pole pieces are connected, or there is a octapole lens system where 8 pole pieces are connected. Pole pieces means like this one, that north south. Here it is a quadruple lens system. That is the reason 4 north and south pole pieces are connected, where the hexapole lens system and octapole lens system 6 pole pieces or 8 pole pieces are connected, and they are connected in a alternating polarities, not the same polarities like your quadruple lens system. So, it will be always that north south it will be connected. Okay. So, this kind of lens system is really helping to correct any kind of aberration and other purposes also. So, now as I mentioned, there is a deflector, electromagnetic lens, and we have stigmator, and finally it is coming the aperture. If you look at here, there is some apertures images are there which is regulating. There will be a small hole, it has some kind of diameter here, and which is helping us to allow the electron beam, and how much electron beam it will go through that sample. This is the diagram where we are showing how the electron beam is passing through the aperture. So, today's class I will stop it here, that how the electron beam is going through the aperture. Next class we will complete this section, as well as we will discuss with the ray diagram how it can converge and give us a different kind of images, how it can focus, how we can get a diverge and converge electron beam using the electromagnetic lenses. Thank you very much for your attention.